All right. Good evening, Physics 11 students. So I've had some questions today about the review, questions in the review. So I thought take this opportunity perhaps to go over how to solve the questions, and maybe I'll just work through them all and put this up there. Some people are having a little bit of difficulty, and that's okay. And so, I mean, this is Tuesday. If you want to put off to Thursday, Friday, just to make sure you have yourself that you have these questions under control. That's fine. As I mentioned in the email, I cannot see the whites of your eyes, and so I'm not sure when you're understanding or if you're not understanding. So please, make every effort as you can to reach out and ask for help. And more than willing to do that. We can do that through Jitsi, or as you can doing this right now, and then you can have opportunity to take a look at it later as you have time. So let's see if we can get things set. Now I should have done this differently. So I'm just looking between my screens so I can have two screens, one cursor, so we can see if we can make this up. So this is the review on gravitational forces. Graffiti. It's going to be a great day, we can tell. Gravity. Sorry, I'm not wearing a Hawaiian shirt. I'm in the off hours, no Hawaiian shirt. So just a quick review. In terms of gravity, we have two equations. We have F is equal to mg. This is for when we are on planet. And G is our gravitational field strength. And that is equal to our 9.8 newtons per kilogram. It is also equal to the acceleration due to gravity of 9.8 meters per second squared. And those two numbers, as mentioned before, are the same because this is how it is defined. The gravitational field strength is defined in terms of the acceleration a mass feels in this gravitational field. So this is when we're on planet. When we're close to a planet, height isn't varying very much in terms of relation to the diameter of, the diameter of the planet and so on. So if we're dealing with things with a couple kilometers high and so on, gravity is pretty much constant through that whole area. If we are jumping outwards and doing different planetary distances, then we can't use this equation. What we have to use is F is equal to Gm1 m2 over d squared, where big G is our 6.67 times 10 to the negative 11. M's are our masses in kilograms, and d is the distance in meters between the objects. And so this is where the force of gravity between any two objects in the universe can be calculated in this way. So the force between you and the sun, between you and the moon, between you and Mars, between you and Jupiter. We could calculate the mass of all these things. Between you and your car, there is a force of gravity, just incredibly small. Either the distances get really large, in which case the force is small, or the masses are relatively small, in which case the force is small. But when you're close to a planet such as Earth, and the Earth has a large mass, your mass, which is fairly small, still exerts, there still is an attractive force between you and the force of gravity. One thing that does come up, and I just want to mention it now, is that you can take forces are always going to be equal to forces. Now, what do I mean? Well, if forces are measured in newtons, well, other forces are also going to be measured in newtons. So sometimes we can take equations and we can uh, learn interesting things about them. So we can take our force of gravity that we would be calculating in a gravitational field strength, and we can take the force of gravity that we would calculate with the planet Earth and so on. And we can make those equal to each other. And so we would have mg is equal to gm, and let's call that mass of the Earth. And then we have the radius of the Earth squared. Well, we have this mass. This is our unknown mass, our test mass. It's just a small mass. But the thing is that we also have that mass over here. This mass, in essence, occurs in two places. So we have the mass within a uniform gravity field, and we have that mass in consideration with the planet that we're on, which means I could divide this side by that mass and divide this side by that mass, and this cancels out, and this cancels out. So that test mass, that small mass, is gone. And so what we have is a definition of what little g is, with g, mass of the Earth, and the diameter, or the radius of the Earth, squared. Sometimes they use r, sometimes they use d. And let's do that. Let's calculate this out. So if we want to know what g is, well, g, big G, is 6.67 times 10 to the negative 11. Mass of the Earth is like, I should have this written down. I should have given this out to you. Actually, you might have it in your, well, I don't know. I don't know. The mass of, and the diameter of the Earth. It's something that is sometimes used, and so it's not unheard of to have that in a table and so on, or on a system of constants. That's not. So you know that I'm doing this ad lib, because if I wasn't doing this ad lib, I would have all this information settled already and know what these are. All right, so the mass of the Earth is 5.98 times 10 to the 24th kilograms. And we need the radius of the Earth in terms of meters. Here, let me look this up. So radius of the Earth, 6,371 kilometers. So we can say that that is 6.371 times 10 to the 6 meters. 6.371 times 10 to the 6 meters squared. So if we plug this into my calculator, we've done things correctly. 6.67, 10 to the negative 11 times 5.98, 10 to the 24th divided by 6.371, 10 to the 6 squared equals, and wouldn't you know it, little g comes out to be 9.83. And we can call that newtons per kilogram. Well, they might say, hey, well, that's kind of cool, except, to come up with this value of 9.83, 9.81, they had to know the mass of the Earth. And how do you know the mass of the Earth? Do you take the Earth, and let's draw a little bit of Earth here. There's America, and you've got Western Canada here, and stuff like that. And they pull out the big bathroom scale, and you put it onto the bathroom scale, and then you measure the mass of it. Hey, and it's 6.31 times blah blah blah. Well, no, that's not actually how they're going to do it. What they're going to be doing is they're going to be working the opposite way. Rather than this can be measured, little g can be measured. We can calculate, and if you think about it, if little g can be measured, because we take the force, or F is equal to mg, and so g is equal to the F divided by our m. So we can measure the force of gravity, we can work out what the mass of that is, and come up with this value of 9.8. And then we can take the radius, and we can take this, and come up with what the mass of the Earth is. And so this is how they weigh the Earth, by understanding what the mass, what the acceleration is due to an object on the Earth. Anyways, so I just wanted to go through this, and it's kind of neat. But yeah, no big bathroom scales in space. Not how it works. Okay, so the first question, we've got a 1 kilogram bird, 1 kilogram bird flying in a 5 kilogram encase made of glass. The combination will weight. All right, so we have our mass of 1.0 kilograms, and so that's our mass 1. We have our mass 2, and that's equal to 5.0 kilograms. So a total mass is 6.0 kilograms. We want to know what the combination will weigh. And weigh always refers to the force of gravity, not the mass. Weight is in newtons, mass is in kilograms. So this will be equal to 6.0, and they say we're going to use a value of g that's equal to 10 meters per second squared. Just makes it really easy. And we get 60 newtons. That's the weight of our, all I can think of is like Tweety Bird. You got Tweety Bird, and there's our bird. Anyways, so that's question number 1, how we work it out. So let's come to question number 2. And question number what would balance the weight of an object with a mass of 60 kilograms? Oh, this is a good one actually to do. So what we have is we've got this mass. I just got to get my pen again. We've got a mass, and we've got this mass, and it has 6 kilograms. So the force of gravity that's acting on this, which is mg, well, that's going to equal to 6.0 times our 10. That's equal to 60 newtons. So, but let's take another look at, because where is that box? Well, that box is, say, sitting on a table. And so we know from our box, we've got this force of 60 newtons going down. And remember that this 10 comes from the acceleration. Is this accelerating? It's not accelerating. But you can think of it as somebody came along and cut through these legs. What's going to happen? Well, the whole thing goes down. I was talking with Tim this afternoon, saying that, well, let's say you're sitting on a chair. Yeah, we all sit on a chair. We all, read a book on a chair. We're sitting smiling. Or maybe there's a cup of coffee or something like that. We're sitting on the chair. The chair holds us up. Yet we've probably seen times where, so hold on, suddenly the chair collapses and we're laying out on the floor. Our cup of coffee is flying up into the air and the coffee is pouring out onto us. Not a good situation because the chair is no longer holding us up. The chair was holding us up. So when we have a situation where we have this block on the block is being pulled down with 60 newtons. The table is providing a force that's going up of 60 newtons. This is actually sort of foreshadowing of part of what we call Newton's laws. Newton's laws of motion. Yeah, because it deals with acceleration. So we're going to have Newton's laws, and that's actually the next unit we're going to be talking about. We're going to be doing lots with forces and understanding really where this comes from. But it's really, really good to understand that you've got a force coming down. The table gives a force going up. And that is where this is going. All right, so let's go on to question number 3. Yes, I'm coming to your questions. In the year 2020, we've got an astronaut will make routine visits to the moon where G is equal to 1.6 newtons per kilogram. The astronaut has a mass of 50 kilograms on the Earth where G is 10. What is the force of gravity acting on, what force of gravity acts on the astronaut on the moon surface? All right, so on Earth, the force of gravity, a little g, that's equal to sorry, no, I'm even misreading this. So we know that on Earth, the mass is equal to 50 kilograms. On the moon, the mass of the astronaut, well, the gravitational field is 1/6 of what it is on Earth. Well, so the mass is going to be like 50 divided by 6 then, right? No, the mass is still 50. Mass is a property of matter. It does not matter. It doesn't matter where in the universe we take a look at what the mass is. The mass remains the same. When I was in high school, I had a teacher say, would you rather have a kilogram of gold on the Earth or a kilogram of gold on the moon? Well, on the Earth, here's my gold. Represents a certain amount. We could work out what the force of gravity is on the Earth. If we took that bar of gold and we went to the moon, the force of gravity is going to be less, still the same amount of gold. We haven't gotten rid of the gold. It's just the force of gravity is less. And if you think of if we were in orbit around our planet, then we talk about being weightless. And that mass of that bar of gold in free fall, in orbit around the Earth, the force of gravity would be equal to 0. But there's still a mass equaling 1 kilogram. So even though the force of gravity isn't acting on it, the force is still there. All right, so let's getting back to this question. So on the moon, we want to know what the force of gravity is. So F is equal to mg. So F is still equal to our 50 kilograms. G now no longer is 9.8, it is our 1.6 newtons per kilogram. And so when we do that calculation, pulling out a Casio FX 260 Solar or your Casio FX 260 Solar 2, times 1.6. I know. That would be equal to 80 newtons. And there we go. Okay. You might have got these answers already, and that's perfectly fine. I just want to go over these and hopefully give you a little bit of background sometimes to these questions. Taking a second look at these questions when people had questions coming up and realized, yeah, there's some aspects in here that are dealing with forces and so on that perhaps didn't come across in the lesson the same way. But that's why we're doing this. All right, so we take a look at question number 4. Question number 4. Now, in two situations, the object is placed on an equal arm balance and requires 12 kilograms to balance it. When placed on a spring balance, the object causes a reading of 12 kilograms. All right, so we got two situations. We've got a spring balance. Now, if you were a fisherman or something like that, you might have one of these things, and you've got your mass here, and you got your spring balance, and the spring measures what moves up and down. They got a little here, moves up and down and says, hey, this is 12 kilograms because this is 12 kilograms. Cool. And we can take a balance beam, basically like a teeter-totter. We put our mass on the end, which is 12 kilograms, and we've got another object over here, which is 12 kilograms, and it balances out. So we know that the masses are equal, the forces of gravity are equal on either end of this balance here. And this is the key thing, because we have a force of gravity here, and we have a force of gravity here, and those forces of gravity and the masses are going to be equal because they're where they are on this balance beam. Well, here, do we have forces as well? Yeah, we do. Because we've got, again, remember, the chair isn't breaking, the table isn't breaking. So if this mass here isn't falling, we know that there's going to be a force of gravity that's going down, but it's being balanced by what's going on in here. So we're going to have the force of a spring that is holding the object up. The spring compresses. Spring forces are what we're going to be taking a look at later this week. So we got a spring force that's going up and balancing the force of gravity going down. And what we do is that we calibrate. We put markings, it's supposed to be calibrate. We put markings onto this scale here, the spring scale, and say, that's 12 kilograms, that's 10 kilograms, that's 5 kilograms, and then we put these markings in between. So we put anything onto there and say, that's 25 kilograms. We can measure the mass, we can measure the weight of that. But this is on Earth. To the moon! And this is why I love physics, because hey, we can say, let's go someplace else in this universe and see what's going on. And let's come over here, because what we had was we had our two masses. And so both of these had the force of gravity going down. Right? So up here, the forces of gravity were equal because the masses were equal. Have the masses changed? No. These two objects still have the same mass. It's a property of the matter. Is the force of gravity different? Yes. But because we have the force of gravity on this side and the force of gravity on this side, the force of gravities are still going to be equal. They're different from where it was in the first because now we're on the moon, but the force of gravity in the moon is still going to be consistent between the two objects. Those remain balanced out. But remember we had a little fishing scale with a spring on the inside? Well, now we put this mass on. Is that still 12 kilograms? Sure it is. It's still 12 kilograms because that's the chunk of matter that we had. That's its property. So we're going to have a force of gravity, but the force of gravity is going to be much less than what the force of gravity was on Earth because it's the lower gravitational field strength. And so the force that the spring has to put into it is going to be less as well. So if this is 12 kilograms, rather than saying, so up here this said 12 kilograms, now it's going to say 2 kilograms. Did we lose mass? No. But the calibration is wrong. Calibration is wrong. So what we have to do is that you have to go to the gift shop. You know, when the rocket landed on the moon and there was that gift shop just inside the rocket port. If you went into that gift shop, then you could buy a moon scale calibrated to the moon's gravitational field strength. And then when you put that onto there, it would measure 12 kilograms because it's been calibrated for the moon. Okay? So calibration here, this is spring scales, different forces. We have to calibrate it for the proper value that it is. All right, so let's come back over and get the next one. Number 5. The gravitational force between, is this going to work? The gravitational force between two objects is always an attraction, depends on how massive the objects are, depends inversely on the square of the distance between them, all of the above. Well, the answer to this is D, all of the above. Because when we're talking about gravitational or the gravitational force between objects, this F, I'm using big G as a subscript, we have G, we have our mass 1, we have our mass 2, and we have the distance between them squared, because we've got M1, M2, and then the distance from centers of mass, that's what we're calling our D. Increase the mass, we're going to increase the force. Decrease the distance, we're going to increase the force. Increase the distance, we decrease the force. But we've got, this is the inverse square. Inverse because it's 1 over, and square because we've got this little uppercase 2 there. The inverse, we talk about the inverse square law. This happens, we see this also in gravity, but also in light. You can think of a candle. Okay, you got this light, and let's say if we were to take beams coming out, beams of light would be coming out like this. So if this here was one length, one distance, then if we were to go set up a screen that was another length away, here, what we would see is that this area here, A, is this area here, this area here, this area here, this area here. You can see that those are all approximately the same size there. And this is where the inverse square law is. So the amount of light that hits here is being, because we've doubled that, we're going to have 1/4 the amount of light with each of these squares. If we went to a third L, then if we drew our screen at that point, what we would find now so this was 1, this is 1/4, and this is now 1/9. Because that all that all corresponds to this inverse square law, where so we could talk about this as being 1 over L squared. That's how the light falls off or over as we move away from that. So gravity follows that, light follows that, and I'm sure there's some other phenomena that also follow that. But the idea of the inverse square is sort of a key thing to that, where we have 1 over. And this is where we have our proportionality. We say our proportionality 1 over the distance between the masses squared. you know, if you actually measured these things, you could see that these squares are all basically the same size. And it's kind of neat. At school, I've got a couple demonstrations. One of them is just taking a light and a piece of paper, and you set up the piece of paper, creates a shadow, and you take a look at the size of the shadow, it takes up 4 pieces of paper. And it's just kind of cool how that works. All right, so that's what we mean by the inverse square law, and that's why those are all of the above. Gee, I'm sorry this is taking so long. But hopefully this helps some of you as we go through. I'm still waiting on faster internet. I would like to apologize for that. We had great hopes, went down to the mailbox, just waiting for the stuff to come in the mail, and we can plug it in, and it would be so much better. All right. So here we have person, long legs. What's the gravitational attraction between a 75 kilogram student and her 1,500 kilogram car? And so we've got this, so 75, we've got 1,500, and they are 10 meters apart from their centers. Center of mass. All right, so this is just going to be F G M M over R D squared. So that's going to be equal to 6.67 times 10 to the negative 11 times 75 times 1,500 divided by 10 squared. It's going to be a huge number. No, it's not. 6.67, 10 to the negative 11 times 75 times 1,500 divided by 10 squared, which is 100 equals, and we get 7.5. 7.5 times 10 to the negative 8 newtons. Diddly squat. Answers A and B were the best bets for that. D is sort of out there. So let's go on to question number 7. What is the acceleration due to gravity at the surface of a planet whose mass is that and whose radius is that? All right, so mass being 1.88 times 10 to the 21 kilograms. And the radius is equal to 4.34 times 10 to the 5th meters. Well, this comes down to where I was talking about the introduction. F is equal to F. Forces are equal to forces. So we can take our mg is equal to our gmm over d squared. And so the test mass drops out. So our gravitational field strength, the acceleration due to gravity, is going to be equal to g, the mass of the planet over the radius of the planet squared. 6.67 times 10 to the negative 11 times the mass of the planet, 1.88 times 10 to the 21 kilograms. That's less than what the Earth is, right? 10 to the 24th, so we're 1,000 times less. So the force of gravity is going to be that much less. And the radius, 4.34 times 10 to the 5th. Well, this is smaller as well. Don't forget to square that. Easy, common thing, like, whoa, make sure you square. It's easy to miss that. Even in your calculations, people will write things out like that and then just fail to do it. So Casio FX 260 solar, 10 to the negative 11, 2 for you, Tim, times 1.88, 10 to the 21, divided by 4.34, 10 to the 5th, squared equals. So the acceleration due to gravity, our G, our A, is equal to 0.67 newtons per kilogram, or meters per second squared. 6.66 they had. And this is I think I was talking about in the movie, or yeah, in the movie, in the lesson I talked about this, where the European Space Agency was sending a space probe onto to come around onto a comet, and they were to land it onto the comet. And the force of gravity was there. The force of gravity was so small that you had this thing like a washing machine came down, bounce, and bounce, and bounced, and bounced, and bounced on the surface of the comet. Really, really hard to land. All right, that was 7. Let's check out 8. In an experiment. All right, coming back to this. So in an experiment, this is 8, conducted on the surface of a planet. Here's the surface of the planet. We have this steel ball, which is 2.6 kilograms, drops to the ground with an acceleration of 7.3 meters per second squared. And what we want to know, what is the planet's mass? If the radius of the planet, so we know the size of the planet, there are ways to do that, 4.8 times 10 to the 6th meters, then what is the planet's mass? Oh, this is cool. Okay, because this here again is forces are equal to forces. So we have our mg is equal to our gm m over our d squared. The mass that we're testing falls out. So it doesn't matter that it's a 2.6 kilogram ball. What we know is that our g for the gravitational field strength for the planet is going to be 7.3 meters per second squared, 7.3 newtons per kilogram. 6.67 times 10 to the negative 11 mass of the planet, and then the radius is 4.8 times 10 to the 6 meters. Don't forget to square it. And so this, we can then do some calculation. We're going to bring this across, divide by this. So the mass of the planet is equal to, so 7.3 times our 4.8, 10 to the 6 squared divided by 6.67, 10 to the negative 11 equals, the mass of the planet comes out to be 2.5 times 10 to the 24th kilograms. Answer is B. Okay, and this goes back again to what we talked about in the beginning. I just want to, how do you know what the size of the planet is? This is really kind of interesting. And you often talk about, well, we know the Earth is actually flat and it's sitting on the back of a tortoise, and that's sitting on the back of another tortoise, and its tortoises all the way down. Well, that's generally not recognized as being correct. In fact, if we can go back to the Greek philosophers, they were able to calculate that the Earth was actually a sphere. And they were actually able to come up with a value for the sphere. And it happened for a guy who was down in Egypt, if I remember. Because, let's go on to this. He knew that on a particular day that there was a well. And a well is where you get water from. And he knew that on this particular day, the sun happened to be straight up, and so there would be no shadow. And so there was a clear, bright spot of sunlight at the bottom of this well on this one particular day. But he knew that, several hundred kilometers, kilometers away, there was another spot. And if you were to take a look, there in the sun, then the sun wasn't straight down, but there was an angle to that sun. And if we take a look, there's just going to be this angle. And so if there's this angle here and there's not over here where there's a certain distance apart, then we can use that information and work out with algebra and some trigonometry that there is a certain radius to this, because here the sun's going straight down, but if we step a stick here, then we can see that there's an angle, and so we'll work out what the radius is. Anyways, they worked out. They were wrong, but hey, the idea was there, and got them going on the right direction. All right. Greeks were pretty clever. There's lots of stuff we don't understand about Greeks. Math they had, well, they took very little, and they were able to do a lot, but they couldn't work out the square root of 1. And that was really a downfall to them. It's kind of interesting to come across problems like that, not being able to do something, coming up with irrational numbers, it sort of stumps them and they don't have a way of answering it. And they've had a very sort of mechanical way of answering these things, and then they can't do it. Mr. Reichel, I'm sure, could give you really lots of information about that, because, he's Mr. Reichel. He's the math. Right, Megan? You guys do math every day, right? Woo-hoo! All right, so we're talking oranges here. Okay, we've got a sack of oranges, a bag of oranges. There's my oranges inside here, and I've got another bag of oranges, and they're bursting out the top, and I got 10 in here, and I got 10 in here. Well, what do you know? There's a center of mass, there's a center of mass. So we have M1, M2, and there's a distance that is between them. And so what that tells us is that there is a force of attraction between these things as well. And that force is going to be equal to G M1, M2 over the distance squared. Okay, so we have these two stacks. And if we knew the masses, and we could actually come up and calculate this, and we'd come up with a very small number. It doesn't really matter, but it's there. But they want to know, what could we do to double the force? So rather than having our force is equal to F, we want to change that to be 2F. So how can we change that to be 2F? Well, G, we can't do anything to G. Can't do anything there. We're keeping the baskets, like when they talk about adding oranges, we're not doing anything to change the distance. So what we're all doing here is that we're changing and playing around with the masses. So we talk about A is adding 10 oranges to each sack, adding 20 oranges to each sack, adding 10 oranges to one sack, or adding 20 oranges to one sack. Well, let's just say that each orange weighed a kilogram. So right now we got 10 kilograms on this side, we've got 10 kilograms on this side, and we've got 10 times 10, so our force is equal to, let's say it's just equal to 100, 10 times 10. So if we wanted to make this 2F, well, 2F would be 200. And how do we get 200? Well, we can go 10 times 20. How did we get 20? Well, we went 10 plus another 10 oranges. So we would put 10 oranges into one of the bags. If, this is wrong, we put 10 plus 10 into that bag and 10 plus 10 into that bag. So this is going to be 20 and 20. We're going to have 20 times 20, and that's going to be equal to 400. No, we didn't want 400. We wanted 200. So we're just going to add 10 oranges to one of the bags. So playing around with this can sometimes help. That's number 9, and this brings us to lucky number 10. Oh, here we go. A gravitational force of 900 newtons acts on a man standing on the surface of a planet of radius r. What is the gravitational force at 3r from the center of the planet? So here's, let me get my pen again. Here's my planet. Here's my astronaut. And we know here that the force is equal to 900. So then we're going to go to 3R. So this is 1R. So here's another R, and then here's another R. So we're at 3R. Wow, remember we said F is equal to GMM over D squared. Or if we can take a look just at the masses, we can say force is proportional to the product of the masses. Or we can say that force is proportional to 1 over D squared, the inverse square. Ding, 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 ding. This is the one we're wanting to take a look at. We want to take a look at how this is proportional to. So we want to know, so I sometimes talk about the force old. My force old is going to be proportional to 1 over D squared. But now we're at 3 times that. So we're going to have 1 over 3D, 3R squared. We're triple the distance. Well, this is going to be equal to 1 over 3 squared times 1 over D squared. Well, 3 squared is equal to 9 times 1 over D squared. But remember, my force old is my 1 over D squared. So my force new then is going to be equal to 1/9 times my force old. So that's going to equal 1/9 times my 900 newtons. And 900 divided by 9 is equal to 100 newtons. 1/9, inverse square. And that's how it's done. All right, so we're going to get a quiz up. We're going to put it up. Tomorrow is Wednesday. If you can get it done the next couple days, that would be good. Hopefully this helps. And again, if you have questions, come see me on Jitsi, and I'm more than willing to try and help you out. Okay? All right, take care. Bye. Oh boy. Life is good. Take care. Bye-bye.